Welcome. This is the lecture for Chapter 33 from our textbook. In this chapter, we will learn about the wave model of light, and we will learn to apply the model to cases of interest. Light has both wave and particle properties. We will utilize three models for light. We begin with the wave model of light describing how light waves spread out and how superposition of light waves leads to interference. We will then turn to the ray model of light, where we will describe light traveling in straight lines. This model will provide a simple framework for gaining an understanding of lens and mirror effects. In the latter third of the semester, we will rely heavily on the photon model of light and examine how it fits into our understanding of quantum mechanics. It will be necessary to learn when to use each model. We begin by defining diffraction. Diffraction is the ability of a wave to spread out after passing through a small hole. Or going around a corner. The diffraction of light indicates that light is a wave. We shall see that a smaller hole causes a greater degree of spreading. As a brief reminder about interference, if two rocks are simultaneously dropped into a pond, creating the ripples shown, the lines are the wave crests. As they overlap, the ripples interfere. At the point marked with a dot, is the interference constructive, destructive, somewhere between constructive and destructive, or is there not enough information to make any claims about interference? Since the dot is drawn at a trough location for both waves, the interference should be constructive. Unlike what is observed for a water wave, when light passes through a large opening, it makes a sharp-edged shadow, as shown here. This lack of noticeable diffraction means that if light is a wave, the wavelength must be very small. When red light passes through an opening that is only 0.1 millimeters wide, it does spread out and will produce a diffraction pattern on a viewing screen, as shown. We note that diffraction of light is observable if the hole is sufficiently small. Let's introduce a few common models of light. The wave model. Under many circumstances, light exhibits the same behavior as sound or water waves. The study of light as a wave is called wave optics. The ray model. The properties of prisms, mirrors, and lenses are best understood in terms of light rays. The ray model is the basis of ray optics. The photon model. In the quantum world, light behaves like neither wave nor a particle. Instead, light consists of photons that have both wave-like and particle-like properties. This is the quantum theory of light. In 1801, a physicist named Thomas Young performed an experiment that strongly inferred the wave-like nature of light. He believed that light was composed of waves, and so Young reasoned that some type of interaction would occur when two light waves met. A coherent light source is instant upon a pair of very narrow slits. The two waves that pass through the slits overlap as they spread out. The overlapping waves then interfere, resulting in a pattern of light and dark bands on the viewing screen. Here we see a plane wave instant on the double slit. The waves then spread out behind each slit and interfere as they overlap. Projected onto the viewing screen, bright fringes appear where constructive interference occurs. Note the difference in brightness as we move away from the bright central maximum. To understand this, we will need to also include the diffraction pattern associated with the slits. But for now, it suffices to understand the origins of the bright and dark fringes, which we will examine now. Here we see the double slits presented to the plane wave and the viewing screen. Since we assume that the distance L from the slits to the viewing screen is much greater than the distance D between the slits, the two rays appear as one when zoomed out this far. We will zoom in on the circled area on the next slide. Here we see the circled area from before magnified to a great enough level that we can see the two slits. Note that both rays passing through the slits are effectively parallel. Since the distance to the viewing screen is so great, we can drop a line perpendicular to ray 1 as it passes through the slit and allow it to intersect ray 2. The angle subtended between this line and the double slit screen is theta. This is the same angle that the two rays will make with respect to the normal to the double slit screen or to the viewing screen. Convince yourself that the extra path length traveled by ray 2 to reach the viewing screen compared to that traveled by ray 1 is then equal to d times sine theta. We will get constructive interference between rays 1 and rays 2 anytime the path length difference is 0 or an integer multiple of the wavelength. We can say that the bright fringes occur at values of theta m such that delta r equals m times lambda, where m equals 0, 1, 2, 3, and so on. Recall that for small angles, tangent theta is approximately equal to sine theta is approximately equal to theta. Since we just said that delta r equals m times lambda, and that delta r equals d times sine theta, we have that m times lambda equals d times sine theta. We can employ the small angle approximation, and then we get that the theta value of the mth bright fringe is roughly equal to m times lambda over d. Since tangent theta would be y divided by L, we can again employ the small angle approximation to say that m times lambda over d should also equal y over L. Rearranging terms, we find that the location of the mth bright fringe on the viewing screen is m times lambda times L over d. For both of these equations, m can take on any integer value, positive, negative, or 0, though your text is only showing the absolute values here. Let's just quickly check in. A laboratory experiment produces a double-slit interference pattern on a screen. The point on the screen, marked with a dot, is how much farther from the left slit than from the right slit. One lambda, 1.5 lambda, 2.0 lambda, 2.5 lambda, 3.0 lambda. Pause the video here and convince yourself of the correct answer and your rationale before proceeding. The answer is C. Remember that the extra travel distance for rays 1 and 2 goes as delta R equals D times sine theta. Maxima, or bright fringes, will occur when the extra travel distance is an integer multiple of the wavelength lambda. The central bright fringe corresponds to m equals to 0. The dot is then on the m equals 2 bright fringe. Ray 2 must have traveled an extra 2 wavelengths compared to ray 1 to produce this fringe, so the dot must be 2 lambda further from slit 2 than from slit 1. Since the dot is to the right of the central maximum, it stands to reason that the nearer slit 1 is on the right and the further slit 2 is on the left. Does this make sense? A laboratory experiment produces a double-slit interference pattern on a screen. If the screen is moved farther away from the slits, the fringes will be closer together, in the same positions, farther apart, or fuzzy and out of focus. The answer is that the adjacent bright fringes will be farther apart after moving the viewing screen farther away. Recall that the location of the mth bright fringe on the viewing screen is m times lambda times L over d. The locations are proportional to the distance between the double slit screen and the viewing screen. If we are given a double slit interference pattern on a screen placed 1 meter behind a double slit screen with d equals to 0.3 millimeters, and we see 10 bright fringes span a distance of 1.7 centimeters, can we determine the wavelength of the light? In fact, we can. The number of spacings between 10 bright fringes is 9. You can convince yourself of this by holding your two hands in front of you with your thumbs adjacent. Count the gaps between your digits and include the gap between your thumbs. We can then take advantage of the fact that the spacing between bright fringes is uniform. This means that 1.7 centimeters is equal to 9 times the spacing between any two adjacent bright fringes, or delta y equals 1.7 centimeters divided by 9 equals 1.89 times 10 to the minus 3 meters. We know that delta y between bright fringes on the viewing screen is lambda times L over D. Solving for lambda, we find that it is equal to D times delta Y over L. Ensuring that D, L, and delta Y are all stated in like units, we find that lambda is about 570 times 10 to the minus 9 meters, or 570 nanometers. The visible spectrum roughly spans from 400 to 700 nanometers, so this wavelength is in the visible portion of the spectrum, as expected. A laboratory experiment produces this double-slit interference pattern on a screen when red light is used. If green light is used instead, with everything else the same, the bright fringes will be closer together, in the same positions, farther apart, or there will be no fringes because the conditions for interference won't be satisfied. The answer is that the fringes will be closer together. Since delta Y equals lambda times L over D, and green light has a shorter wavelength than red light, the value of delta lambda would be smaller for green light than for red light, holding everything else constant. A laboratory experiment produces a double-slit interference pattern on a screen. If the slits are moved closer together, the bright fringes will be closer together, in the same positions, farther apart, there will be no fringes because the conditions for interference won't be satisfied. The answer is that the fringes will be farther apart. Since delta Y equals lambda times L over D, the value of delta Y would be larger as D is decreased, while holding everything else constant. Looking at our stock example double-slit interference pattern, you might have noticed it dimming as we move off-center. Here is a plot of intensity as a function of position on the viewing screen. Note that in our analysis thus far, we would expect that the bright fringes in the double-slit interference pattern would all have the same intensity. In practice, this is not true as you have just noticed in our example pattern shown thus far. The intensity of the double-slit interference pattern at position Y is equal to 4 times I1 times cosine squared of quantity pi times d times y over lambda times L and quantity. But why is this so? We will attempt to develop an explanation in due course. Suppose we were to replace the double slit with an opaque screen that has n closely spaced slits. When illuminated from one side, each of these slits becomes the source of a light wave that diffracts or spreads out behind the slit. Such a multi-slit device is called a diffraction grating. Bright fringes will occur at angles theta m such that d sine theta m equals m lambda, where again m can take on any integer value. The y positions of these bright fringes will occur at ym equals L tan theta m. The figure shows a diffraction grating in which n slits are equally spaced a distance d apart. This is a top view of the grating, as we look down on the experiment, and the slits extend above and below the page. Only 10 slits are shown here, but a practical grating will have hundreds or even thousands of slits. The wave from each slit travels an extra path length delta r equals d sine theta farther than the wave from the slit above it. We find that bright fringes then occur at angles theta m such that d sine theta m equals m lambda, where m can again take on any integer value. The y positions of these bright fringes are equal to L times tangent theta m. Diffraction gratings are commonly used for measuring the wavelength of light. If the instant light consists of two slightly different wavelengths, each wavelength will be diffracted at a slightly different angle. Here, blue and violet are separated out. Since blue has a longer wavelength than violet, it is diffracted slightly more. In a laboratory experiment, a diffraction grating produces an interference pattern on a screen. If the number of slits in the grating is increased, with everything else, including the slit spacing, the same, then the fringes stay the same brightness and get closer together. The fringes stay the same brightness and get farther apart. The fringes stay in the same positions but get brighter and narrower. The fringes stay in the same positions but get dimmer and wider. The fringes get brighter, narrower, and closer together. The answer is C. If the slit spacing and width is unchanged, the positions will not change, but recall that the intensity is proportional to n squared. Example 33.2 from your text is a good example of the utility of diffraction gratings. Light from a sodium lamp passes through a diffraction grating having 1,000 slits per millimeter. The interference pattern is viewed on a screen 1.000 meters behind the grating. Two bright yellow fringes are observed 72.88 centimeters and 73.00 centimeters from the bright central maximum. What are the wavelengths producing these two yellow fringes? Here we see a representative schematic of the experimental setup, though using blue and violet light. We will assume that m equals 1 here since the problem does not mention other yellow lines. We return to our statement that theta equals inverse tangent of y over L. Plugging in values, we find that the 72.88 centimeter fringe corresponds to an angle of 36.08 degrees, and the 73.00 centimeter fringe corresponds to an angle of 36.13 degrees. Since lambda equals d sine theta with m equal to 1, we have that the two wavelengths are 589.0 nanometers and 589.6 nanometers, respectively. In practice, most diffraction gratings are manufactured as reflection gratings. The interference pattern is exactly the same as the interference pattern of light transmitted through n-parallel slits. Reflection gratings are produced by etching parallel grooves into the surface of a mirror. Naturally occurring reflection gratings are responsible for some some forms of color in nature. Here we see a peacock feather and a micrograph image of a small section consisting of nearly parallel rods of melanin, which act as a reflection grating. Diffraction through a tall, narrow slit is known as single-slit diffraction. In single-slit diffraction, a viewing screen is placed a distance L behind the slit of width A, and we will always make the assumption that L is much greater than A. We turn now to Huygens' principle. Here we see a representation of a plane wave. The essence of Huygens' principle is that every point on the wavefront is itself the source or seed of a spherical wavelet that travel at the speed of the wave in a given medium. Here, the new or later wavefront is the tangent to all of the wavelets. Since the wavelets all expand at the same speed in the medium, the new or later wavefront here is parallel to the initial wavefront. If instead we have a spherical wavefront initially, the wavefront at some later time will be tangent to each of the wavelets, and the new or later wavefront will be spherical as well. We can apply Huygens' principle to justify the single-slit diffraction phenomena that we discussed at the beginning of this lecture. Here, a planar wavefront is instant upon a narrow slit of width A. Each point of the initial wavefront may serve as the seed of a spherical wavelet. The wavelet from each point on the initial wavefront overlaps and interfere, creating a diffraction pattern on the viewing screen. The figure shows the path of several wavelets that travel ahead to the central point on the screen. The screen is so very far to the right in this magnified view of the slit. The paths are very nearly parallel to each other. Thus, all the wavelets travel the same distance and arrive at the screen in phase with each other, leading to constructive interference at the center of the viewing screen opposite the slit. In this figure, wavelets 1 and 2 start from points that are a/2 apart. Every point on the wavefront can be paired with another point distance a/2 away. The two wavelets in these pairs have a difference in travel distance delta r equals to a/2 times sine theta. If the path length difference delta r equals lambda/2, the wavelets arrive at the screen out of phase and interfere destructively with each other, effectively canceling out pairwise and creating an interference minimum. The light pattern from a single slit consists of a central maximum flanked by a series of weaker secondary maxima and dark fringes. The dark fringes occur at angles theta dark equals P times lambda over A, where P is any positive integer. If a helium neon laser, which has wavelength of 633 nanometers, passes through a narrow slit and is seen on a screen 2.0 meters behind the slit, and the first minimum in the diffraction pattern is observed to be 1.2 centimeters from the central maximum, how wide is the slit? Here is a sketch of the situation. We first apply the small angle approximation to find that the angle to the first minimum is theta 1 is roughly tangent theta 1 equals 1.2 centimeters divided by 200 centimeters equals 0.00600 radians, or 0.344 degrees. Since the first minimum occurs at theta 1 equals lambda over A, we find that A, the slit width, is about 0.11 millimeters. The central maximum of this single slit diffraction pattern is much brighter than the secondary maxima. The width of the central maximum on a screen a distance L away is twice the spacing between the dark fringes on either side, or W equals 2 lambda L over A for a single slit. The farther away from the screen, larger L, the wider the pattern of light becomes. The narrower the opening, smaller A, the wider the pattern of light becomes. Another quick check-in question. A laboratory experiment produces a single slit diffraction pattern on a screen. If the slit is made narrower, the bright fringes will be closer together in the same positions, farther apart, or there will be no fringes because the conditions for diffraction won't be satisfied. The answer is that the bright fringes will be farther apart from one another. Recall that the locations of the minima are at y dark equals P lambda L over A. As A is reduced, the values of y increase. If light passes through a 0.12 millimeter wide slit and forms a diffraction pattern on a screen 1.00 meters behind the slit, and the width of the bright central maximum is observed to be 0.85 centimeters, what is the wavelength of the light? Solving our prior equation relating W, lambda, L, and A for lambda, we find that the wavelength is approximately 510 nanometers. A laboratory experiment produces a double slit interference pattern on a screen. If the left slit is blocked, the screen will look like pattern A, B, C, or D. The answer is D. B is simply half the original double-slit interference pattern, which is clearly not correct. But can you reason why it is not A or C? To analyze double-slit interference, we can use a phasor diagram to show the addition of two electric field vectors. The projections of the phasors onto the x-axis are what we would add in a superposition calculation. If we add the phasors as vectors using the tip-to-tail method, the magnitude E of their vector sum is the electric field amplitude of the superposition of the two vectors. E equals the absolute value of the quantity 2E cosine of delta phi over 2 end quantity. Figure A shows a slit of width A with n point sources of Huygens wavelets, each separated by a distance A over n. Figure B analyzes the diffraction at the center of the diffraction pattern, where each arrives in phase. Figure C is the phasor diagram for superposition at an arbitrary point on the screen. The angle of the last phasor is beta equals n delta phi adjacent equals 2 pi a sine theta over lambda. E is then the amplitude of the n wavelets. To determine E, we allow n to approach infinity. This makes our calculation exact, and it also makes our calculation easier, because now the chain of phasors with length E0 is simply the arc of a circle. From the geometry, the angle subtending this arc must be beta. The amplitude of the superposition is E naught times sine of pi a sine theta over lambda divided by pi a sine theta over lambda. And the intensity of the superposition is I naught times the quantity squared of sine of pi a sine theta over lambda divided by pi a sine theta over lambda, end quantity. Here is the resulting intensity of the single slit diffraction pattern. Note that this matches our expectations. We earlier calculated the ideal double slit intensity for two slits separated by distance d, but each slit has width a, so the double slit pattern is modulated by the single slit diffraction intensity for a slit of width a. Thus, in practice, the double slit intensity for small angles is then I double equals I naught times the quantity squared of sine of pi ay over lambda L divided by pi ay over lambda L, n squared quantity, times cosine squared of pi dy over lambda L. The cosine term produces the fringe oscillations, but now the overall intensity is determined by the diffraction of the individual slits. If an interference maximum falls exactly on a minimum a 0 in the single slit diffraction pattern, then we have what is called a missing order. The condition then for a missing order would be that m lambda over d would need to equal p lambda over a. The lambdas on both sides cancel, and we can solve for the missing order as p times d over a, where p is any positive integer. Another common diffraction case is that of a circular aperture. Light of wavelength lambda passes through a circular aperture of diameter d and is then incident on a viewing screen a distance L behind the aperture. L is much, much greater than d. The diffraction pattern has a circular central maximum surrounded by a series of secondary bright fringes shaped like rings. The angle of the first minimum in the intensity is theta 1 equals 1.22 lambda over d. The width of the central maximum on the screen is then W equals 2y1 is roughly 2.44 lambda L over d. Here we see an infographic for the intensity of a diffraction by a circular opening, as well as a representative example of a diffraction pattern by a circular aperture. When light passes through an opening of size A, the angle of the first diffraction minimum is about theta 1 equals inverse sine of lambda over A. Light waves, because of their very short wavelength, almost always have lambda over A much, much less than 1 and diffract to produce a slowly spreading beam of light. In the accompanying infographic, we see the difference in resulting diffraction spread for two cases. One where lambda is approximately equal to A, in which case there is a high degree of diffraction, and a second case where the wavelength is significantly smaller than the aperture, A, in which case the beam does not spread out nearly as rapidly. If light travels in straight lines, the image on the screen will be the same size as the hole. Diffraction does not become important unless the light spreads out over a diameter larger than d. When light passes through a hole of diameter d, if the spreading due to diffraction is less than the size of the opening, then use the ray model and think of light as traveling in straight lines. If the spreading due to diffraction is greater than the size of the opening, then use the wave model of light. The crossover point between the two regimes occurs when the central maximum width of a circular aperture diffraction pattern is equal to the size of the opening, namely 2.44 lambda L over dc equals dc. For visible light of roughly 500 nanometer wavelength with a screen separation of roughly 1 meter, dc becomes roughly 1 millimeter. Here we see an excellent summary of the wave model of light. We make use of this primarily when diffraction is an important consideration. We have that light is an EM wave traveling through vacuum at speed c, such that the product of its wavelength and frequency is c. Light exhibits diffraction and interference. The ray model does do a better job modeling experiments in situation where diffraction is negligible. Typically, use the wave model for apertures less than a millimeter in size, and the ray model for openings exceeding 1 millimeter in size. A device that uses interference to make very precise measurements is called an interferometer. Interference requires two waves of exactly the same wavelength. One way of guaranteeing that two waves have exactly equal wavelengths is to divide one wave into two parts of smaller amplitude. Later, at a different point in space, the two parts are recombined. Interferometers are based on the division and recombination of a single wave. Here we see the Michelson interferometer. Note that the wave is divided by the beam splitter, which could be as simple as a half mirror. Half of the beam then reflects from mirror 1, while the other half reflects from mirror 2, which can be moved back and forth with a micrometer. The two beams are recombined and then detected. The resulting superposition of the two waves, traveling different paths, can then be observed. In a Michelson interferometer, the phase difference, delta phi, between the recombined beams is due entirely to the path length difference between the beams. Delta R equals 2L2 minus 2L1. Constructive interference will occur when L2 minus L1 equals m lambda over 2, and destructive interference will occur when L2 minus L1 equals quantity m plus half end quantity times lambda over 2. These equations are valid at the center of the beam. There is a bright or dark center spot on the detector when the first or second equation is true, respectively. The photograph shows the pattern of circular interference fringes seen in the output of a Michelson interferometer. If mirror M2 is moved by turning the screw, the central spot in the fringe pattern alternates between bright and dark. The number delta M of maxima appearing as M2 moves through a distance delta L2 is delta M equals 2 delta 2 over lambda. This infographic shows one method of recording a hologram. Note that a coherent light source is provided by the laser. The beam is split, with part providing a reference beam and the other part reflecting off of the object to be recorded. The reflected part and the reference beam interfere, providing specific information about differences of travel path. Below is an enlarged photograph of a portion of a hologram. It's certainly not obvious that information is stored in this pattern, but it is. The holographic image is recovered by sending the reference beam through it. The diffracted reference beam reconstructs the original scattered wave. As you look at this diffracted wave, from the far side of the hologram, you see the object exactly as if it were there. The view is three-dimensional because by moving your head with respect to the hologram, you can see different portions of the wavefront. Okay, that is all for today. As always, you are all awesome. Have wonderful days. Thank you for stopping by. Don't be strangers. Enjoy your days, but not so much that we don't see you next time.